Madras. Later, his excellence continuum made him get an admission into another prestigious institute, IISc Bangalore, and got his PhD awarded in the year 2014. Later, he continued his research excellence as a postdoctoral fellow at University of Chicago in USA. In the year 2017, Dr. Rajib joined IIT-Tirupati. His research interests includes spectroscopy modeling, machine learning, water desalination using artificial water channels. Dr. Rajib Biswas, having 28 publications, national and international journals, and handled two projects funded by DST, guided good number of students, scholars, attended and organized several conferences, and delivered good number of invited talks. With this few lines of introduction, I take the honor of inviting Dr. Rajib Biswas to deliver his talk to our enthusiastic students. Now I hand over the session to our guest, Rajib Biswas, sir.
Thank you, madam. Thank you for a very kind introduction. Now I will try to share my screen, if you allow.
Okay, sir. Thank you, sir.
Is it visible?
Yes, sir.
Can you see my slides?
Yes, sir.
Is it in full screen mode?
No, no.
Let me check again. Share it again. Okay. How about now? Can you see the slides in full screen mode, madam? Can you please confirm?
Yes, sir. It's visible, sir.
It is full screen mode, right?
The slides are on slide, sir.
No, you can see in full screen mode. Full screen mode.
Yes, sir.
Right?
Yes, sir. Yes, sir. Yes, sir. You can continue, sir.
I will continue then. Okay. Fine. So, a very good morning to all of you. So, as far as I understood, this talk is rather than a scientific lecture. I mean, the more of less of a research-oriented lecture than of a tutorial. So, I thought of giving you a broad overview and then showing a couple of examples so where this computational chemistry can help us to understand many complex phenomena. So that's why the very broad title I put for this today's presentation is Molecular Modeling and Classical Simulation Approaches, the domain which I am working on. So presently, as madam suggested, I am working on diverse area of theoretical and computational chemistry, starting from water desalination, theoretical spectroscopy, and protein function and their structure, dynamics, and many more. So these are the three main subdomains I am working, but there are several other small projects which my students comes and they are free to do whatever they are willing to explore. Now, as far as this computational chemistry concerned, if anybody wants to learn the subject, these are the few books they can go through and they will be able to understand the crust of the problem and they'll be able to do the molecular modeling by themselves. For example, the computer simulations of liquids and molecular simulations, these are more of a simulation perspective books, and the other one, the statistical mechanics for chemistry and material science, is a book for the background scientific foundation which leads us to molecular simulations. Any problem, madam?
No, sir. No, sir. You can
Okay.
continue, sir.
Yeah. So okay. So this computational chemistry has been developed many. Madam, can you ask them to mute? Otherwise, it becomes very
Yes, sir.
disturbing.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Yes, sir. Sorry for the disturbance, sir. Naresh,
No
sir.
problem. I understand.
Yes, sir. I'll call him, sir. Naresh, sir. Can you ask the student? Can you mute the student, sir? Yes, sir. I think they have
Sorry.
muted, sir.
Sorry.
You can continue. Sorry,
Okay.
sorry for the disturbance, sir.
So yeah, so the computational chemistry has developed a lot, and it has achieved several landmark discoveries, and which has been awarded by the best prestigious awards, which is we know is the Nobel Award. The first Nobel Prize in the computational chemistry domain was awarded to Walter Kohn and John A. Popple for the discovery of density functional theory. And since their discovery of density functional theory, the density functional theory has been developed, and now almost in any material science or organic chemistry reaction mechanism or biological complexes, their understanding of enzyme kinetics and other things, people are using this density functional theory based approach, and then it has been matured a lot after their seminal discovery. And almost a decade back, the domain which I'm working on, the classical approaches and multi-scale modeling,
Rajiv, sir. Sorry, you are muted, sir.
I think some problem from your side. I'm getting muted automatically. I don't know why.
Yes, sir. Yes, sir. We will resolve, sir. Give me 1 minute, sir.
Sure,
Sir,
sure, sure.
everybody in mute, sir. You can continue. Sir,
Yes,
okay, you may
I
continue now.
think now I am audible, and
Yes, sir. You're
yeah,
audible.
only Tirupati Rao sir is uh, on. I mean, he has to mute. Yes, then I can just go ahead. Yeah, please.
Yeah. Yes, sir. Thank
So
you.
just give me a second. I'll share.
Oh,
I think I am okay. Madam, can you once confirm that you are able to see the slides?
yes, sir. Yes, sir.
Okay. So at any time, if I am, you are not hearing my voice, please alert me, because I am not able to see the Microsoft Team. I have
Yeah.
just make it full screen. Okay. So
Okay,
the
sir.
thing I was talking about, that this year the Nobel Prize was awarded in both chemistry and physics and artificial intelligence. Particularly in the case of chemistry, it was been awarded to three professors. I mean, one professor and two scientific personnel who are working in Google. So Professor David Baker from University of Washington and Dr. Demis Hassabis and John Jumper for the development of artificial intelligence-based platform which can predict protein structure and can facilitate drug design and protein-protein interaction in a different dimension. So the molecular modeling can be used plenty of systems and subject areas. So from that I'm just pointing a couple of them. So for example, the first figure which I am just enlightening is now is the multi-component vesicle with protein inclusions. You can study how the protein is going actually inside that vesicle. This is the water desalination setup, how the polluted water can be purified using this kind of artificial water channel based setup. And this is some simple sodium chloride solutions. How do you understand the solution structure of different ions in aqueous system? In this kind of coarse graining modeling, so where we reduce the description of full atomistic model to a some kind of in a spherical beads and all, and then we reduce the computational cost, and that has also been developed over the several years. So this is carbon nanotube based setup for water desalination or gas separations. Many applications it has. And this example I'm showing is that water osmolytes interactions. Osmolyte is a very small organic molecules which can help us to stable or destable biomolecular macromolecules. Okay, and this in this example I'm just showing how protein ligand and talk with each other. So these all are the examples. How do you study? So these are nice figures and nice setups I just showed, but how do you make it? So to know that, we have to understand a little bit about molecular modeling. So what do we mean by molecular modeling, and why we want to study molecular modeling? Molecular modeling is actually can help us in different directions. For example, if you would like to understand the molecular interactions, protein ligand interaction, protein protein interaction, DNA or RNA dynamics, that can be studied using this molecular modeling. Drug designing, for example, a particular small molecules, whether it is going to a specific place and binding to the affected area, and a drug DNA intercalation, and then we can actually screen several small molecules and find out the efficacy of one or two couple of such small molecules as a drug agent, which can actually reduce lots of time and money, because if we would have to do experiment for those many molecules, we have simply waste a lot of chemicals, and it will be time consuming. So computational chemistry can guide us and help us to a more directed drug discovery as well. And if you would like to study from different length scale, for example, if you would like to study from atomic to macromolecular, let's say I want to study in the atomic length scale how the electrons are actually forming chemical bond, I can study that. How do you want to, if you would like to simulate skin cancer, people are doing skin cancer simulations, so that can also be done. It's a huge, humongous amount of atoms and molecules are involved in case of if you would like to simulate a skin. And the time scale is the time scale we are talking about with the reference frame of the molecules or atoms, how they are moving when we have started our simulation. From second to second time scale to couple of milliseconds, we can go with the today's computational physics. And the best part of molecule, you have the information for each and every individual molecule at your hand, so you can tune and probe single molecule level interactions with different other molecules or what they are doing. And actually this molecular modeling can complement the experiment techniques. For example, several spectroscopic techniques, infrared spectroscopy, UV visible, crystal, X-ray crystallography, or even in case of microscopy, we get an ensemble picture. That means the overall macroscopic response we get. So we don't have what are the molecular arrangement giving rise to those kind of. So to understand why we are getting that particular shape of a spectroscopic signal, modeling can or computer can help. What is molecular? So molecular modeling should put it in one line with references. It says that molecular modeling is science and art of studying molecular structure.
Sir, your voice muted. Sir, Biswas sir, check your voice.
Okay, I don't know why it is getting muted. I have no idea.
Sorry for
Now it is okay, sir.
disturbance, sir.
It is just automatically getting muted. I have. Okay.
Now it
So
is okay,
let
sir.
me. Okay. So is it sharing now?
Yes, sir.
Yes, sir,
Okay,
you can
great.
proceed.
So now, the if it is mute, no, please let me know. It is automatically getting muted.
Sure,
So
sir.
if it is, yeah. So uh, what is model? So model is when we try to mimic the real system. If a model behaves like exactly the real system, then it is no longer a model. It is the system itself. So that nice philosophical analogy can be correlated with a famous quotation by Pablo Picasso. So in which he told that we all know that art is not truth. Art is a lie that makes us realize truth, at least the truth that is given us to understand. So the artist must know the manner whereby convince others of the truthfulness of his lies. So molecular modeling is not the real system. It is a model by which we want to understand the truthfulness of a real system. For example, based on the phenomena we are looking, based on the system we are looking, the model can be different for a same molecule. For studying different phenomena we are interested. Molecular modeling can be very simple. We can actually model the atoms or molecules like this one. These ball and stick models are very popular, and I hope all of you know it, because this is kind of in classroom our teacher used to bring this, and then they used to teach us by building several molecules from this individual fragment. So that's the same thing we do in computer. We just tell that the molecules, each individual atom may be spherical beads, soft beads, or hard beads, and they are connected by either a rigid rod or a harmonic spring, or their shapes are different. For example, they may be elliptical in shape. So all those things we just introduce to describe the molecules, and to formulate their interactions, we just based on we take help of several mathematical expressions, so which I will be talking about in the next couple of slides. So before too much detail to this molecular modeling, so there are majorly classified into two different approaches. One is in the atomistic approach, atomistic domain, which is ab initio methods, which we would like to use if you want to study the electronic properties at a very accurate way. And if you are not really interested about the electronic properties that accurate way, but you are more of a interested about the macroscopic responses of the large molecules like proteins and biomolecules, then you can go for semi-empirical methods where you will be describing the molecules using some classical models. So two approaches can be combined, and you can actually address many different multi-scale systems using these two different approaches. Now, there are some simulation methodologies which are available at today's days, but I have just pointed out a couple of them which can be handy when you would like to study some small molecules or even a biomolecules. The first and foremost one is the molecular dynamics simulations, where one can study the dynamics. That means atoms and molecules will be dancing, and then you can explore them as a function of time. And the second one is the Monte Carlo simulation. So time is not there, but you will be exploring the configurational space. For example, if you would like to space or place a molecule in a glass of in a glass or inside a beaker, what you need to have three coordinate point x, y, and z. That will give you one particular reference point. But we all know, if we are talking about a solution, they are not static, they are just moving. So in addition to the position, you need another dimension, which is velocity or time as a function. Position is a function of time. So these two things together can be simulated in molecular dynamics, but only the instantaneous snapshots. That means the instantaneous molecular configuration can be simulated using Monte Carlo technique. So there are docking simulations. You can use small molecules or small peptides, small ligands to dock into a big protein molecules, and they are or enzyme to specific active sites and study their binding energies and what efficacy of their that complex. So that can be used to do drug discovery. A lot of anti-cancer research is being done by using these docking simulations. And the quantum mechanics and molecular mechanics simulations, where a small portions of your system will be treated using quantum mechanical description, in which you are really interested about the electronic degrees of freedom. That means maybe the reaction is happening at that center, and the rest of them are just doing normal dynamics, and you are not worried about the electronic degrees of freedom. So there you can just compartmentalize your simulation setup, where the small segment of your simulation box can be treated with quantum mechanics and the rest can be treated with molecular mechanics. There is another method called cross-grain simulations. If you are willing to do a very big protein molecules, for example, as I in the beginning I told, if you want to simulate skin, or maybe the COVID virus, full COVID virus, or the HIV virus, or any virus you name it, they are very big. So with full atomic descriptions, it is impossible to simulate with a reasonable trajectory length. So for that, another approach came up. So where you couple in chemically similar molecules or groups, chemically similar groups into one larger particles, and that reduces the computational cost, because now in addition to those many atoms, you are having big groups. So the information data needed and then computational cost becomes really cheaper than compared to the all atom simulations. So there are some methods which is known as enhanced sampling techniques. For example, the life is as like human being, life is not always a very smooth highway. It might have several mountains and hills, and some potholes might also be there. So where you will get stuck. So if you are stuck, some push is needed to overcome that difficulty in your life. Same goes for the molecules. Molecules, the potential energy surface is not very smooth. They are very rugged in nature. They have several local minima and global minima. So the molecules are very prone to stuck in the local minima. So if you are, for example, if the system is very viscous, and if you would like to study the system at very low temperature, then the simulation dynamics will be very low, and they will be stuck at some local minima in the potential energy landscape. So to sample the entire potential energy landscape, then only you will understand the actual properties, thermodynamic properties of that particular molecules. You need some help, some push. Somebody has to come from the outside. So that technique is known as enhanced sampling technique. There are another methods which is known as free energy calculations, which actually gives us energy associated with many molecular transformations or binding. So for example, if I would like to study the proton transfer, so how the proton is going from one acid to the other water molecules or some other base is abstracting that proton. So as a function of the distance, you can find out the energy cost. What will be the energy barrier for that proton transfer reactions? Or maybe I'm just having two small protein molecules immersed in a one beaker of water, and I want to understand how likely they are going to come and form an association. So you can just scan that the protein-protein interaction energy as a function of distance, and then you can find out that energy barrier, how much is the protein binding energy. That can also be done using these free energy calculations. There are many more simulation methodologies, as you can understand. So I have just pointed out a few majorly used these simulation methodologies in these slides. And what are the length scales and time scales we are talking about? If we are going for particularly this ab initio or quantum level, we can go for up to some picosecond time scale, couple of hundreds of picoseconds using some a couple of hundreds of atoms, maybe 256 atoms. You can just go for 100 picoseconds with this very high computational power. And there are some reactive molecular dynamics where you can go for sub-nanosecond, and then you can actually simulate a little bit bigger system than this ab initio MD. And classical molecular dynamics, where all these electronic descriptions are gone and reactions are not allowed. Your molecules are just a frozen molecules, or maybe maximum the bond can vibrate using some harmonic or anharmonic description. So that's there you can do actually some millions or even billions of simulate atoms at today's date, and that can you can go up to microsecond time scale. So coarse grain you can go even bigger, and if you want to do some continuum study, for example, if you are from mechanical engineering, you want to study fluid flow, and if you are from civil engineering, you want to study how the concrete crack is happening, all those things if you want to study, then you can even go to this continuum description as well. So
Excuse
here
me,
is the
sir.
same thing. How?
Excuse me, sir. The slide is not seen, sir.
Okay. Let me see why this is happening. I don't understand. Now?
Yeah, sir. It's coming now.
Okay. Thank you, madam.
Okay, sir.
So, and then as a function of year, how this has been evolved, that you can see. So in 1990s, we can only do some couple of nanometers. Now we are going for some billions of atoms. This is the full capsid photosynthesis chromatophore can be simulated today's date. So now, which one to choose? Whether you want to choose the quantum mechanical simulation approach or classical simulation approach, it totally depends on the phenomena you are looking for. If you are interested in a reaction, then of course you have to go for either quantum mechanical descriptions or this reacts FFMD. If you are not interested about quantum mechanical description of that means reactions, then you can fairly go with the classical. But if you are interested about reaction and also you want to study a very big molecules, then you go for a mixed, that is QMM, quantum mechanics plus molecular mechanics. Now, how to choose whether my system is very big or very small? That means how big is too big and how long I have to simulate. This is not the computational time. This is the time with respect to the with respect to the I think I have to share. Yeah, with respect to the time scale we are obtaining by solving some equation of motions, that time scale we are talking about. So now in case of quantum mechanical simulations, we can maximum go up to 256 water molecules, and that can simulate up to 100 picoseconds because their scaling is very bad. The scales goes with number of electrons in cube or n to the power 4. So they are horribly computationally expensive. And the dt, that means the integration time state, can be sub femtosecond. And as far as classical MD concerns, you can go some only one processor if you use in your desktop or workstations. You can go up to 50,000 atom and simulate 1 nanosecond without any issue. But if you are using a HPC, high performance computational facility, then you can go for billions of atoms, and then you can go for microsecond as well. Now, how molecules stop? Because we are talking about these ball and sticks, nice drawing, and then we are just putting them inside the computer, but they have to interact, right? Otherwise, how do you know whether they have to come very close or they have to go away, or whether they have to be very friendly or they have to fight with each other? All those information you have to give. So this one, I just quoted Richard Feynman.
Hello.
Where they he just mentioned in his the famous Feynman lecture series that I believe it is the atomic hypothesis that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. That means when the molecules are far away, they can feel attraction, but when you are bringing them very nearby, they will feel repulsion. So now, if we just apply our high school knowledge that, if we think about the molecules, they are consist of several atoms, and if we just go down in the atom description, they have a nucleus which has a positive charge, they have an electron cloud. Now, if you would like to bring two atoms together, they will feel attraction if they are of opposite polarity up to certain extent. They will not feel repulsion. So they will settle down at some equilibrium distances, which we call as a bond distance. That is forming a chemical bond. But if you further reduce down, they will feel their electron cloud each other, and which is of same polarity. So they will repel, and then there will be huge repulsion. Now, to describe these different sets of interactions, the molecular interaction has been broadly classified into two sets of interaction. One is intramolecular, that means within our cell, that is known as bonded interactions. Okay, so that is bond stretching. If we are forming a chemical bond, so please understand the image whichever I am showing, this is just a representative image, or whatever drawing we see usually in our textbooks, that is not the drawing of a chemical bond. It's just the notion that there exists a chemical bond. For example, for any chemical bond, we cannot put it as a line. It's just the density, probability density of electron. It's just density. You cannot put it as a line if you think about in quantum mechanics, in terms of quantum mechanics. Okay? But then again, we have to do something, right? So these bonded interactions is divided into bond stretching. For example, all these, this is at the CH3 and CH2. This is just a polymer I have just showed here. And then for three atoms, they will form a angle, which is known as bond angle. And for four atoms, they will form another angle, which is known as dihedral angle, which determines the shape of the molecules, macromolecules. Okay. Now, if they have some polarity, some charge are there, they will interact with each other using the our most common understanding way of interacting. Two charge ions are electrostatic interactions, right? And if they are neutral in nature, they will have van der Waals interactions, dispersions and van der Waals interactions. So these are non-bonded interactions. So that means they are intermolecular. Non-bonded interaction are intermolecular, and the bonded interactions are intramolecular. Now we have separated out the the molecular interactions in two different parts. Now let us just go ahead and use a simple mathematical model to treat them. So this is one of the very celebrated potential energy function which we routinely use to model van der Waals interactions and dispersion interactions in molecular simulations, classical approach. Okay. So where it has two parts, the blue part is repulsive in nature. You can see it is positive. If you bring the two atoms very close by, it will shoot up, and the red part, it is having a negative sign. It is inattractive in nature. So that is the tail portion, and this is the down one. This is the attractive domain, and if beyond that, if you just try to squeeze in, it will just shoot up the energy. So this is the potential energy functional which we use to model the van der Waals interactions. And this is just the Coulomb interactions which describe the electrostatic interactions, where we just model each atom with a static partial charge. In terms of quantum mechanics, this is not a true description of electron density, because the density should be scattered over all over the place. But here we are just making an assumption that all the atoms are having point charge, that they are sitting at the center of the atom. So having said that, in classical modeling we do this, and if they are of same polarity, they will have this kind of red graph behavior, repulsive in nature. If they are of opposite polarity, that is cation and anion, they will attract, and this is really in long range in nature. Now, in case of bonded interactions, if we understand, for example, if you have two balls and connected with a spring, that can be the very simplest way of mimicking a chemical bond. So that's what we do in the classical simulation. So we just say all the chemical bonds are nothing but a harmonic spring. They are actually vibrating around some equilibrium bond distance, which is R0, and with some force constant. So based on the nature of the bond, if it is single bond, the force constant will be a little bit less. But if it is a double bond, then the force constant will be a little bit higher. Even for triple bond, it will be even higher. Okay. And there are many chemical bonds which are anharmonic in nature. That's why in this plot I showed both harmonic as well as the anharmonic nature. But most of the chemical bonds are harmonic, except some small system. For example, water. Although we model with a harmonic description, but water do possess an harmonicity in bond stretching energy landscape. So in case of angle, we use the same the harmonic potential energy functional form, so which can actually have your three atoms which will oscillate, and then they will try to have a equilibrium bond angle theta naught. Okay. So there are another term I told four atom terms. So 1, 2, 3, 4, four atomic terms, which is known as dihedral, which actually gives us different conformations of big molecules. For example, if you talk about ethane, whether it will be a Gauss conformation or eclipse conformation, that can be arise from this torsional angle potential, and it can be of very various form. Here I just showed using a cosine series, but it can be harmonic, it can be combinations of both cosine and sine. Many different forms are available in the literature, and based on your molecules of interest, you can choose one. Here I just showed one for the purpose of showing one example. So now total potential energy you have to find out, because end of the day we have to find out what is the energy of your system, right? So as I told, broadly you have classified intermolecular and intramolecular. Intermolecular is bonded, non-bonded, and intramolecular is bonded. You just add them because energy contribution is nothing but additive, and that will give you the total potential energy. So this is not your true total Hamiltonian. Hamiltonian is having both kinetic energy part as well as the potential energy part. But this potential energy will be handy because this potential energy will be used to evaluate the force, where we need to solve the Newton's equation of motions, which is nothing but F equals to ma, where we need the force, right? So if you get force, which is nothing but the negative derivative of potential with respect to coordinate, that will give us force, and from the force we can get the acceleration of each individual molecule. And if you just integrate the accelerations, then you will get velocity. So that will give you velocity. If you know the velocity from a small time duration where the molecule will be, you can predict it. So that's why molecular dynamics is known as deterministic method. You can determine where these molecules will be from one frame of information to the next frame. So all these equations, you see there are some coefficients which are fixed. For example, R naught, KB, this theta naught, K angle, and this KT, this is N, and then gamma, and then QI, QJ, here epsilon ij, sigma ij, all those things are a constant. They are constants. So these constants are known as force field parameters. So from the experimental value or experimental available data, and on top of that some high level quantum mechanical calculations will help us to find out what would be the value for KB, what would be the value of R naught, theta naught, and all those things. So a table which consists of all these constants values are known as force field parameters. So these parameters are very specific to each and every individual molecules. If you are simulating a water molecules, and if you are going for a particular force field, you have a set of parameters. If you are going for another molecules, you have a different set of parameters. So these are the key ingredients of your molecular simulations or molecular modeling methodologies, which will make your equation to behave like that molecules. Okay. So these sets of parameters are known as force field parameters, and as I told, it has all bond lengths, angles, force constants, partial atomic charges, and the Lennard-Jones parameters, which is nothing but the van der Waals parameters. Some examples of force fields are amber, charm, bromose, OPLA, sol atom. For biomolecules, they are routinely used. Even you can use for small molecules as well. But there are for organic ligand, particularly, some force fields are generated, which is known as GAF and CGEN-FF. This has been done by charm people. And coarse grain models, where you reduce the atomistic description, you make one methane as a one sphere, maybe ethanol as one sphere for the methyl group, and CH2 group the another sphere, and you have OH. So like that. So that is known as Martini. And polarizable force field. So here in the classical force field, what we did, we just told that the atomic charges are static at the center, but when all the different polarity of atoms come closer, they should rearrange. They should have a little bit of alterations of the charge density and their position. So that is known as the polarizability. So that information is missing in the standard classical force field. But if you would like to include that, there are some force field. One of them is amoeba. So that can be used to include the polarizable force field. Now, what is molecular dynamics? So again, I just borrowed the Richard P. Feynman's quote that everything that living things do can be understood in terms of the jigglings and wigglings of atoms. That means the way atoms are dancing, if you can understand that, almost all phenomena in our chemistry world can be understood, or we can have a certain amount of understanding regarding the phenomena as well as the system. So if we just dissect the two terms, molecular and dynamics, dynamics and simulation. So dynamics is motions, all of we know, and simulation means what? We are trying to mimic something. We are trying to mimicking the actual chemical system using this computational methodology. So that means we are mimicking the actual chemical system and we are trying to understand their motions. So we will understand the chemical or the dynamical behavior of any particular systems of our interest as a time dependent manner, and we will solve the Hamiltonians for that total systems, which is nothing but a classical Hamiltonian. Do not just get confused with the quantum mechanical Hamiltonian. These are two completely different things, but in a nutshell, same thing: potential energy plus kinetic energy. But the way we take into account the potential and kinetic energy, they are different. Now, how do you get the time dependence? Here we have to solve Newton's equation of motion. So there are many equations of motion, but one routinely uses Newton's equation of motion. That's why I put it here. Okay. What do? You just set up initial coordinate. Give, for example, I have, let's say, some couple of water molecules I would like to simulate in the simulation box. I give them some initial positions and then I assign them initial velocities, because if I don't give initial velocities, they will not have any future prediction. So I have to initialize that, and then we calculate for that particular set of coordinate points what will be the potential energy. From the potential energy we get the force, which is nothing but this F equals to minus negative gradient of our potential energy. And from the force we get accelerations, and if you just integrate that, you will get velocities, and from the velocities you will get new configurations. So that all these new configurations, and these will keep on repeating until and unless we are satisfied with the amount of time length we have simulated, and then whatever we have asked, if that time is achieved, we will stop our simulation. So this is the same loop will go again and again and again until and unless we reach to the endpoint of the simulation as defined by us. So these are the same thing using just another box diagram. Now, in case of computer simulations, if you think about a bulk response, even one mole of water will have Avogadro number of molecules, right? 10 raised to the power 23. That's a huge number of molecules. So to do that many number of molecules and to this bulk kind of behavior is computationally very expensive. Now, of course, people can go for billions order, but even then, 10 to the power 23 is pretty high. So, what is the alternate then? People have come up with many different assumptions. One such assumption I'm just showing here, which is nothing but periodic boundary conditions, where you divide the system into a very small box, which is, let's say, this central box, where you see all these 5 magenta balls and 1 blue balls are moving, and that is what your system is. Now we construct several mental replica. These all are mental replica. They are not real system. Okay, we have started with only 5 or 6 balls, and we have mentally constructed infinite dimensional system. Now this is known as periodic boundary conditions. Our system is repeated periodically in infinite number of boxes. So that is actually with a less number of molecule, we are achieving the bulk like of behavior. So this is a very smart assumption people have come up with, and there are some way of treating the potential energy, and this is in a one shot, one image, static image, which can be seen the periodic boundary condition. You see, from this central box, if the one particle is going this directions, from the other image it will come from the opposite side. So as if the number of particles are always constant in one box, but there is no surface. So if you consider the total number of molecules, only this 5 and nothing else is there, so there are some almost all the molecules or particles will be surrounded by vacuum, so which is not a bulk behavior. In case of bulk behavior, all the molecules should be surrounded by other molecules, right? So this is the smartest assumption people have done, periodic boundary conditions, and then to take into account the potential energy contribution in a proper way, there is another thing which is known as minimum image convention. So you construct the minimum image out of all these periodic images, and then you take into account potential energy and kinetic energy. So this is kind of just the introduction and brief foundations. Whatever I thought of discussing, it is done. Now I will just go quickly. One or two examples where we have used these methodologies in our laboratory. Recently, we try to understand the one of the biologically motivated osmolalite, which is known as trimethylene oxide. So this is TMAO, and TMAO is an osmolalite which helps marine organism to be live at very deep down in the sea. If you understand, if you go down to the sea, as you are going down, the hydrostatic pressure will be huge. So right now we are living at 1 atmosphere pressure, but if somebody is squeezing us with a huge amount of pressure, we will not feel comfortable, and after a certain point of time, a certain amount of pressure, we all will die. But at the deep down, even several kilometers deep inside the sea level, where the pressure goes to 1,000 bar or 10,000 bar, there marine organisms are live. You can find live fishes. So how they are live, how their protein structure are intact. It's a very wonderful. Nature has chosen this small osmolalite, this TMAO. It has been found that in their body, 4 molar TMAO concentration is always there. So that TMAO is helping that protein to not be denatured or not to go to some other conformation rather than the biologically active configurations. Okay. So this is the motivation of exploring this and how this TMAO is actually interacting with the water molecule. So we have studied using this molecular dynamics technique and the theoretical spectroscopy methodology. And another osmolalite is the urea. So water urea is also another very well studied osmolites which actually destabilize the protein structure. It is known as denaturant agent. Okay. So if somebody wants to study unfolding mechanism of a protein, they can put experimentally, they can put some concentration of urea solution and the protein will be denatured, and then you can study the denaturing state, denaturing event. So now in case of water urea solution using the infrared spectroscopy, it has been found that no matter what is the concentration of your urea inside the water molecules, the IR spectrum signal of water doesn't change. So why it is not changing? IR spectrum should actually reflect the local environment change. Infrared spectroscopy, right? If you have a local dipole moment change, it should be reflected in the molecular simulation or actually in experimental data as well. So we try to probe that. We use this theoretical spectroscopy technique where we chose a very small clusters of urea water, and then we went ahead and built a theoretical spectroscopy setup, which is like this way. We took the classical empty trajectory and then find out those small spherical clusters, and then we just mimic the isotopically dilute infrared spectroscopy responses using one single OH oscillator as a probe. Then we just did that for only one single OH oscillator quantum mechanical calculation. Now you are seeing I am using both classical mechanics as well as quantum mechanics. So it is based on the phenomena I am looking, right? Here I am looking for vibrational spectroscopy. So I have to go for quantum mechanical treatment. Okay. So that's why we went ahead and then did some quantum mechanical calculations, and we built this spectroscopic model, and then from there some parameters which we have find out, which is nothing but transition dipole moment. If you just go back and check your theoretical spectroscopy books, you will find this is the response function which is responsible for the experimental IR spectrum. Okay. Now with that we have developed the OD response in 10% HOD D2O experimental by mimicking the experimental data. You can see this is our simulated spectrum, and this is the actual experimental spectrum. Of course, the peak position is shifted, but if you just overlap them, almost they are doing very good job in almost 9% of cases. Of course, there are some this high frequency region is there which is not actually matching with our simulated spectrum. Okay, so yeah, this is expected because as I told, if the model behave exactly similar to the system itself, then it is no longer a model, then it is the system itself. So this is the lacuna of our model. But having said that, we can go ahead and find out whether in our theoretical spectroscopy modeling, we can actually predict the urea water based on urea water concentration, it is changing or not. We also found that it is not changing, and then we try to understand why it is not changing. We have divided all the water molecules based on the solvation shell. What do you mean by solvation shell? When you have this one single OH oscillator, that will be surrounded by several water molecules. If they are the first layer, that we call as the first solvation layer. For the second layer, we call the second solvation layer, and the third layer, third solvation layer, so on and so forth. Okay. Now, this solution cell can be constructed based on urea or based on the water we are looking at. So here we have constructed based on the urea because we wanted to understand whether urea actually giving any positive impact to the solution shell of our this OH oscillator. So we surprisingly find that even the first solution shell, all of them are behaving exactly same to the bulk water. So we try to find out the hydrogen bond strength in different region. We found there exists different hydrogen bond strength, but then we found that the population of these hydrogen bond structures are very less. So although the hydrogen bond strength was little bit different, but their population is very less. So as a whole, we are getting this kind of macroscopic response, which is not actually changing any the hydrogen bond the local structure. So this is, we found a nice correlation with the angle and the distance between this urea oxygen and water oxygen. The frequency is nicely correlated, and the hydrogen of water oxygen, and oxygen of urea also it's nicely correlated. But in case of nitrogen, it is there doesn't exist any strong correlation. So we found only in the in case of OU, that means if you go back and see the urea structure, which is CONH2. OU means I am talking about this oxygen, and NU means I am talking about these two nitrogen. So you can see they are bonded with these two hydrogen atoms. So they are not exactly talking in a much more prominent manner than this oxygen. This oxygen is talking much more prominent manner. So that influences gives a very positive impact on the water spectral signature. But having said that, as I told, we also did the two-dimensional free energy hydrogen bond energy calculations, and we found almost similar hydrogen bond energy in case of water and water urea. So this I will just skip a little bit, and I will just go quickly. Madam, how much time do I have?
Sir, you can continue, sir. You can continue. You
Hello?
can take some. Yes, sir.
Am I connected?
Sir, you can continue.
So.
Yes, sir. Yes, sir. You can continue, sir. We have some
Hello?
time, sir. Yes, sir. Hello?
Am I connected?
Yes, sir. Yes, sir.
You're
Hello?
connected, sir. Hello?
Yes,
You are
sir.
in
You
call,
can
sir.
continue.
Hello?
Sir, are you hearing me?
Am I audible? Hello?
Yes, sir. Yes, sir. Yes, sir. You are audible, sir.
Let me see. Maybe one.
Rajiv, sir.
Hello?
You can continue, sir. You can continue.
Hello?
Sir, you can continue, sir.
Okay. I was having some problem. Fine. Thank you.
Okay, sir.
Okay. So this one, another small example I will give based on the water desalination project. So we all know that present day the biggest problem is potable drinking water. So the main culprit are us. We are populating the surface water, and that is actually growing to the groundwater, and then making even the groundwater toxic. So there are many heavy metals and industrial waste which is actually going inside the water molecules, associated with water molecules, and it is becoming a very challenging problem to handle. And then it's not, everything is not come to an end. So there are very active research is going on to battle this emergent situation. So if you go near to the Chennai sea beach area, you will see there is a huge reverse osmosis plant has been set up, which is actually giving the main drinking water supply to this city. And so fortunately sea is there, so huge amount of water is there, but as we know, sea water is coming as not as a pure water, it just mixed with sodium chloride, so it is the salinated water. So if we can come up with some membrane or some other way of purifying that salinated water in a much cost effective manner, that can give us a alternative solution to this problem. So here in our lab we try to find out some nanoporous graphene based membrane and their local structure of the pore. For example, here all this membrane we just functionalized with this OH functional group, and then their symmetrical and asymmetrical arrangement, whether that is actually hampering the effectivity of the water desalination. The setup is this: you have two piston, and this left hand side piston we are applying very high pressure, because as we know, if we just have a semi permeable membrane to a concentrated solution and a pure water solution, the water will always go from the low concentration solution to the high concentration one. So it will have this kind of directions, but we want the other direction, so which is known as reverse osmosis. So the reverse osmosis, if you would like to have it, we have to overcome the osmotic pressure barrier. So we have to apply some pressure, then only the water will go from the concentrated region to the low concentrated region. So there we apply a pressure, and this is our nanoporous graphene sheets. There is a small hole and the water will pass from there. So, and you can see this is the small movie which is showing that the water is actually passing from this side to that side, and these purple color balls and the yellow color balls are sodium and chloride ions. And this is being done recently with one of my student Hema Hassan, and we have found a remarkable result that actually this arrangement of your hydroxyl group play a non-zero role of water permeation, and also particularly in the case of salt rejection. You see, in case of symmetric arrangement, the salt is getting passing more. So this, if it is a smaller number, that is a better membrane. So symmetric is actually performing better. But in case of asymmetric and reduced asymmetric membrane, what do you mean by asymmetric and reduced asymmetric? These two membrane, you see, this is asymmetric and this is reduced asymmetric. Asymmetric means you have just one CH and OH alternate, and that asymmetry you have just reduced a little bit because we just introduced one more CH bond. But here these three OH groups are symmetrically arranged. In between them we have 5 CH bonds. So there we found that actually in terms of salt rejection, symmetrical membrane is behaving better. So then we went ahead and did many different analysis. And this I will not go into deep, but I will just show you the water density, how it is passing from one membrane to the another membrane. You can see the density of water in case of symmetric membrane is pretty high. They are in the same scale. So if it is more red, that means more amount of water is getting passed. But it is less red, that means if it is going more towards the blue side, less amount of water is getting passed. So there is a little bit of difference than symmetric and asymmetric and reduced asymmetric. So the orientation doesn't play a role, that also we have checked. So having said that, I will just conclude with one more example. So this is another example which I don't want to talk. Yeah, so that is this one. So which is the protein, metalloprotein. We are working on this metalloprotein. We just understood this is a very, very stable protein. To melt it, or in other way of to denature it from its native structure, you have to raise the temperature up to 80 degrees Celsius, where most of the protein denatures above 40 degree or 50 degrees Celsius. But here you have to go up to 80 degrees Celsius. This is a very, very thermally stable protein. So we want to understand what is the molecular origin of this thermal stabilization. We found this there exist 8 beta sheets, and all these spheres are nothing but the hydrophobic domain, which is actually creating a amalgamated hydrophobic, beta barrels kind of structure. So that is helping this protein to be stable. Another stable factor is coming from this disulfide bond, and there is a metal ion. As it is a metalloprotein, there is a copper ion here sitting, which is a pentacoordinated. 3 bonds are very strong and 2 are weak bond. So this copper, if you remove, that also actually helps in its a 3-dimensional structural integrity. So this we have done with some advanced sampling technologies, which is known as replica exchange molecular dynamic simulations, where we do several temperature simulations at the same time, and we try to talk with them periodically, and then try to exchange the information between different temperatures replicas, and that help us to explore the potential energy landscape at a faster rate. So this one we found that energy, the intermediate structure of unfolding events of this particular protein. This is 300 Kelvin. This is a native structure. Slowly we are increasing the temperature. You can see it is getting melted. So all these, beta sheets are yellow colored, these kind of stripes, and alpha helix are this kind of purple helical pattern you can see, and all the coil like things are, extended conformation or in a coil structure, which are not either beta sheets or alpha helix. So if you just increase the temperatures, and we found that 420 Kelvin is the melting temperature of this, the simulated melting temperature as far as the simulation concerned, and we found at 420 Kelvin the protein is actually going in the extended conformation. Now this protein has also been found, shows some anti-cancer behavior. So now if we would like to understand the cancer is the just nothing uncontrolled cell growth. So there is one protein molecules which is known as p53, which is suppresses the tumor growth, and this azurine, the metalloprotein azurine, which I just talked about, and its derived peptide, a 28 amino acid sequence from this azurine is found to be very much efficient in restricting several cancer growth or several tumor growth in case of several cancer patients. This is actually under trial 1 phase in the US, and then people are working on to understand its molecular mechanism and to enhance its efficacy. So we try to understand the same the anti-cancer behavior of azurine, and we took this p28 amino acid residue. We found that in addition to this p53, this is the p53 amino acid protein, which if it is binds with p28, it doesn't go bind with another protein which is called as HDM2. So that actually reduces its tumor suppression behavior. So we found that in addition to that, this p28 also can sit and make a dimer with this, or make a interaction cluster with this HDM2 that can reduces its tendency to form the cluster or the complex with p53. That actually help us to give a non-HDM2 mediated anti-cancer properties of these small amino acid segments, which is known as p28. And we did the docking study, and then we found this sets of 3 molecular interaction arrangements are prominent, and we found their energetics, and we showed by doing classical molecular dynamics a huge amount of up to 200 nanoseconds, all these complexes are stable. So with that, I will just stop by acknowledging all the work which has been done by my students. Most of the protein related work was done by Albin. He has submitted his thesis. He is just waiting for me. And Devendra Reddy has graduated. He is now doing postdoc in US. Pankaj has done this urea work, and this is Hema Hassan is doing the water desalination work, and other MSc students also have contributed. This is our campus, and I should also acknowledge all the funding agencies, and thank you all for your kind attention. So madam, over to you.
Thank you, sir. We are very delighted to have you, sir. Now it's time for word of thanks. First, I would thank our distinguished speaker, Dr. Rajib Biswas, sir, for enlightening us through his valuable insights. No doubt, sir, You have inspired us, and hope our students also get inspired with your valuable information that you have given today. And I thank my heartfelt thanks to the management of Aditya University for the immense support in encouraging the team chemistry to organize such fruitful and informative webinar. I immensely thank our Pro Vice Chancellor, Dr. M. Srinivas Reddy sir, for his strenuous guidance in making this event happen. I would like to thank our Vice Chancellor, Dr. M. B. Srinivas sir, and our Pro Vice Chancellor, Academics, Dr. S. Ramasri Madam, our Registrar, Dr. G. Suresh sir, and our Dean School of Engineering, Dr. Dola Sanjay sir. All the deans, not only these, all the deans, HODs, and team chemistry members for their support and presence in making this event a grand success. I thank all the non-teaching staff and admin staff and hardware for their helping hands in making this event go in a smooth way. And finally, I thank Dr. S. Somesh sir for his guidance in arranging this webinar. I thank all the students for being here, having patience, listening, and once again, I thank Dr. Rajib sir for enlightening our faculty as well as students. And in coming future, we expect our students to have your scholars, sir. Thank you, sir. Thank you for being
Thank
with
you
us.
very much. If anyone has a question, I'm okay. I can answer a couple of questions, not an issue.
Yes, students, if you have any queries, you can just ask, sir. Only few students could join, sir. We wouldn't give access to all the students. This is the first
Okay.
time we are organizing a webinar from Aditya University, sir. And we have introduced computational chemistry as one of our topic so that students will be knowing that so much work is being done in chemistry using computers. And with your today's webinar, we could get enlightened and we could know that so much of work is being done. And thanks for making student understand to the basic level of computational chemistry, sir. As I know, it is a research level topic, and you made it so simple that each and everyone could understand. Thank you, sir. Thank you for being with us. We are very grateful for you.
Thank you, madam. Thank you. Hope to visit the campus sometime.
Yes, sir, sure.
Yes.
We are very delighted to honor you in the campus, and most probably in coming days, we will arrange an online, instead of online, it would be an offline session. Then it will be more fruitful. And I
Yes.
hope in the coming days, we will have the session, sir. Thank you, sir. Thank you for being with us.
Thank you, madam. Thank you. Thank you all.
Thank you, sir.
So I will take a leave, madam, then.
Yes, sir. Sure, sir.
Thank you. Thank you.
Thank you, sir. Yes, it's time to say bye, and we will meet soon after this. Okay, thank you, students. Thank you, faculty members. And once again, I thank Team Chemistry for having this wonderful session. So we made this session very successful. Thank you.